Let's use complex numbers to derive one of the most commonly used trigonometric identities. I'm going to start off with a diagram. First, we're going to draw the unit circle in the complex plane. So this over here is going to be the unit circle, and the radius is 1. This over here is the origin, or 0. Along here is the real axis, that's the horizontal axis. I'm going to label that as the real component of a complex number z. And up here I'm going to have the imaginary axis. That's the vertical axis. And this guy I'm going to label imaginary component of z. So this is the center, that's 0. This guy over here is 1. This is I. And this is minus I down here. And on the left, we have minus 1. So all 4 of these guys lie on the unit circle in the complex plane. But we're interested in not just these simple numbers over here, but we're interested in any possible number that could exist on this complex plane. So I'm going to choose a point over here. This is just for convenience. It could be anywhere on the unit circle. So this point is going to lie over here. And we can assign to it a real component and an imaginary component. So I'm going to draw a line going from the origin to this complex number, and we're going to call that complex number z. So this is z over here. And z has some angle, that is theta. And what we can also do is we can take the complex conjugate of z, and the complex conjugate is just going to be the reflection of z over this real axis. So it's going to be the mirror image. And we're going to go down here, and this down here is the mirror image of z. And this guy has a negative angle. It's got an angle minus theta. So this is positive theta upwards, and we've got minus theta going downwards. And this guy we're going to call the complex conjugate. I'm going to put a little star next to z. So we have z and z star. So how do we find the magnitude of a complex number? So the magnitude of a complex number, well, actually, you know what I'm going to do the square of the magnitude first, and then we'll talk about the magnitude. The magnitude is denoted with these vertical bars. So it's like the absolute value sign. But this guy just tells you the magnitude. So it doesn't care about this angle. We're only interested in the length of that vector. Though it's not really a vector, it's a complex number living in the complex plane. So the length of this vector, we know these guys have to be 1, but for any complex number z, we actually can do this. So what we want to do is we want to find the square of the amplitude, or the square of the magnitude, and that's going to give us this expression over here. What we can do is we can multiply by the complex conjugate. So if we take z and we multiply by z star, that's going to give us the square of the magnitude. So this is kind of like squaring a real number. So if you have 3 and you multiply it by 3, that's going to give you 9. So what we have over here is we're taking the complex conjugate and then we're multiplying it. And that's going to give us the square of the magnitude. So this works for all real numbers. And real numbers are a special type of complex number. They lie on the real axis, which is the horizontal axis. And they are actually equal to their own complex conjugate. So for real numbers, these guys are just equal, and we just have the normal relationship where squaring a number is the same as multiplying a number by itself. So the complex plane makes this a little more complicated because there's an imaginary component as well. So if we limit our kind of understanding of this to just complex numbers that live on the unit circle, then what we're going to have to do is we're going to have to write these guys in terms of exponential form. So let's write these guys in terms of e to the I theta. We want to take that form because that's going to be a very convenient form to work with. So let's write this guy. Let's say z is equal to e to the I theta. Then we know this guy, z star, which is the complex conjugate of z, that is equal to e to the minus I theta. So this is what complex conjugation does to this form, where we have e to the I something. So this complex exponential form is very easy to complex conjugate. All you do is you change that angle to a minus sign. And that's the same as reflecting it over the real axis. So this is the mirror image. These guys both have the same real component, but their imaginary components are negatives of each other. So the negative of this guy's imaginary component is this guy's imaginary component. And both of these guys have the same magnitude. And their magnitude is actually 1 because we're limiting all of these complex numbers. They have to live on this unit circle. And if it lives on the unit circle, then its magnitude has to be equal to 1. So let's go ahead and substitute this into this expression. So if we want to find the magnitude of z, that's going to be equal to e to the I theta times e to the minus I theta. And what's going to happen over here, we can use exponential laws and combine these guys together. And what we're going to get is e to the I theta minus theta. And theta minus theta, that is 0. So what we have is e to the 0. And what is this equal to? This is just equal to 1. So we know that this square magnitude is equal to 1. And from that, we can infer that the magnitude has to be equal to 1. We're only taking a positive solution over here because the magnitude is defined to be positive. If you were to actually use negative numbers for the magnitude, then you'd have things going backwards through the origin. And we don't need to do that because the angle already takes care of all of those possibilities. So we can define the magnitude to be a positive value, except when it's equal to 0. If the magnitude is 0, then you're sitting on the origin. But that's actually the only point that causes problems. The origin is sometimes a very tedious point to work with. So what do we have over here? We have found what we already know from the visual intuition. We have found that the square magnitude of a complex number that lives on the unit circle has to be equal to 1. And we found that by writing it in terms of e to the I theta, and then taking the complex conjugate and multiplying. And we used some exponential laws, and we found this conclusion over here. Because e to the 0, that is equal to 1. Now, what I also want to do is want to show you how we can derive that trigonometric identity. So that's the whole purpose of setting up all of this understanding. So what we have to do is we actually have to write this in terms of cosines and sines. And then we can get an equivalent expression, and that's going to be equal to 1. So we know that this is equal to 1, but what we want to do is we want to expand this algebraically and have some expression that involves cosines and sines. So let's do that. If we do that, that's going to give us this. We can have e to the I theta times e to the minus I theta. And that's equal to, what is this left-hand side equal to? Well, this is equal to cosine of theta plus I sine of theta. What about this term on the right? This guy is exactly the same as this, but it has a minus sign over here because it's a complex conjugate. When you take the complex conjugate, you have to negate the imaginary component. So we're going to multiply by cosine of theta minus I sine of theta. And what is that equal to? Well, that is equal to this guy times this guy gives us a cos squared. So I'll write that down over here. Cosine squared of theta. And this guy times this guy, we have a I and a minus I. So I times I is going to give us I squared, which is minus 1. And that minus 1 is actually going to cancel with this minus sign. So you're going to have two minuses, and that's going to give us a plus. So that's going to give us plus sine squared theta. And what's happening to the mixed terms? Well, these terms, when they combine together, they're going to give sine theta and cos theta with an I out the front, and these terms are going to give the minus of that. I'll write it out in full, just so you can see all the cancellations that occur. So from these middle two terms, we're going to get I times sine theta, cosine theta. So that's this term over here, sine theta and cosine theta. And what I'm going to do is actually I'm going to keep this bracket open, and I'm going to add one more term, and that term is the negative of this term, because we have an I, and we have minus sine theta times cosine theta. So we have sine theta and cosine theta. I'll close the bracket over here. So you can see that this evaluates to give 0, because this is just the negative of this. So the inner terms and the outer terms actually cancel. And you can actually see this as the difference of two squares. But it's not a simple difference of two squares because we have a plus sign over here. And that's why these imaginary components actually become very, very useful. So I and minus I multiply together to give us this plus sign over here. So we have plus I and we have minus I. We multiply those guys together, that's going to give us 1. So that's why we have a positive sign over here. So we found that multiplying these two exponentials together gives us cosine squared plus sine squared theta. But we know that this is equal to 1. We found that this is equal to 1. So what can we conclude from this? We can conclude that, I'll write it over here, we can conclude that the cosine squared of theta plus sine squared of theta is equal to 1. And that is one of the most commonly used trigonometric identities. And we've derived that from our understanding of complex numbers. So we started with the unit circle. We looked at complex numbers that live on the unit circle. Then we defined the complex numbers in terms of the complex exponential. In terms of this form over here, we have e to the I theta. And we also defined the complex conjugate. We multiplied the complex number by the complex conjugate, and that gave us the square magnitude. And the square magnitude is equal to 1. And also the magnitude is equal to 1, because 1 squared is equal to 1. So this guy is equal to 1. And then what we did is we expanded e to the I theta and e to the minus I theta into this form involving cos and sine, and that actually gave us this algebraic manipulation. We managed to cancel out this term over here because these mixed terms, they cancel each other out, and we're only left with these positive terms over here. So if you input any angle around over here into this expression, you will always get 1. This is one of the most important things that you should definitely memorize. Some of the other trigonometric identities are not actually very useful to memorize. Some of the really long ones, you can always work them out. You can always derive them, or you can look them up. But this one, because it's so common and it appears everywhere, you should definitely memorize this. Cos squared of theta plus sine squared of theta is equal to 1. And what you should also be familiar with is how to derive it. See where it comes from. This is saying that the real component squared plus the imaginary component squared, that's always equal to 1. So this is actually saying the equation of the circle, right? Because we're on the unit circle, and this is actually another way of understanding the equation of a circle. The equation of the circle says that the Pythagorean distance, right, the Euclidean distance, is actually constant, and it's equal to 1 for a unit circle. That's why this is equal to 1. So how do we know that? Well, this is just the horizontal component squared, and this is the vertical component squared. So it's just Pythagoras' theorem, or the Euclidean distance. So this is definitely something that you should be familiar with, and definitely something you should memorize. It's going to come up a lot. So make sure to check out the other videos in the quantum mechanics playlist. We're going to keep talking about the useful mathematics that we need to understand quantum mechanics. You can find other videos like this one if you click over here.